Hi, let's continue about transport phenomena in biological systems. Now we want to discuss about transport across cell membranes and among cells, and talking about the general physiological transport systems. So first, transport across cells. To regulate the movement of molecules into and through cells, we need a specialized mechanisms. So in addition to diffusion, transport is governed by interactions of solutes with specialized proteins. So ions and small polar molecules such as glucose, sodium, and amino acids have actually low permeabilities across lipid bilayers, which has a hydrophilic head, which faces to the water, and inside there is a hydrophobic part. And so these ions and small polar molecules are transported by, we need a transport proteins, either channels or carriers. And transporting larger molecules inside to the cell that by itself cannot permeate across transmembrane. That phenomena of invagination and engulfing of these molecules into the cells, we call endocytosis. Of course, the opposite is exocytosis. So this is just a reference material, but to give you some idea of the modes of transport across the cell membrane. So first you can see these gases, oxygen, carbon dioxide, and ethanol, which is alcohol, and urea, and these small uncharged polar molecules can freely pass through the cell membrane. So that's, we can see that our breathing and that respiration, oxygen, CO2 have to pass cell membrane freely, and alcohol again. And water has a small permeability, but if slightly permeable, but the bulk motion of water requires a channel. And larger polar molecule, so these are so-called passive diffusion, which means it follows concentration gradient. So gases and these can freely diffuse across the plasma membrane. Passive means it doesn't require any energy and it follows from higher to lower concentration. While a little larger polar molecules such as glucose and ions, which has a charged particle such as calcium or magnesium or chloride ion, and that requires these specialized channels or that we call facilitated diffusion, because still this will go to a favorable concentration gradient. So the membranes slightly permeable to water, but bulk water movement, this is very important, and there needs a specialized water channel called a aqua, as meaning water, aquaporins are used. And the active transport, which you can see active means, you see the famous example as a pumping molecules against their concentration gradients, such as sodium, potassium, this transporter. See, typically in, outside of the cell, sodium concentration is about 10 times higher than inside. In comparison, potassium is higher inside, intracellular, about 10 times higher than the other. And you look at these transporter, this transporter actually brings sodium and potassium ions against their concentration. So it actually requires energy, and that's what ATP hydrolysis is happening here. So that we call active transport. So let's then consider about trans-cellular transport. So two major types of cells regulate the transport of molecules within and between tissues, and through the cell, the transport, such as in the, especially when you get into capillary. So those cells that lines cavities of organs and tissue interfaces, such as the lining, inner lining of stomach, intestines, and lungs, kidneys, liver, and secretory glands are called, of course, epithelial cells. Epi means on top. While those cells line the interior surface of especially blood vessels or lymphatic vessels. And these cells regulate transport like epithelial cells. So it belongs to category of epithelial cells. But in addition, because this one have additional functions such as regulating coagulation in case of there's injury to prevent leakage or loss of blood. And the other is the adhesion of leukocytes. So this is important for function for immune system, and that we call endothelial cells. So here comes a picture for a cardiovascular system as an example. So very important function of a number of our organs and organ systems is in fact transport of molecules that require for our growth and nutrition and repair mechanism and communication within the body, such as hormonal transport. So that such an example is here cardiovascular, and the next page respiratory system and digestive system and renal system. All these many physiologically important organs are in fact their function is a lot about transporting molecules. So here is respiratory system, which brings oxygen into our cardiovascular system and take off those carbon dioxide and the waste. While the other is a digestive system, you can see that it brings the nutrients into our body through this gut system and through the uptake inside epithelial layers of the gut, and that gets into the liver, and then nutrients can be absorbed. And also renal system is movement of our waste products outside of the body. So these are all like transport of molecules. So that's why understanding transport phenomena is fundamentally important to for basic of this. So here, I already talked about this one, but I want to review this again because it's such an important topic, tracer balance in the body. So for example, a drug molecule, for example, is ingested in food and passes out of body in the urine. And that phenomena, let's having some simplifying assumption. So first, tracer is unchanged its original form during passes through the body, which means it's neither generated nor consumed by chemical reactions. So let's just assume this. And then there's no more introduction of tracer into our body during the period of observation, which is at time 0 tracer intake, and then over the following times, there's no introduction. And disappearance of tracer, let's assume our body is, secretes this, the output rate is proportional to the amount of the tracers remaining in our body. So in this case, we can assume this as a first order kinetics. And mathematically, this can be described as this, you remember the systems approach, the accumulation on inside the system boundary of the tracer molecule will be increased by this input flux minus output flux plus the net generation, which is generation minus consumption. Let's assume, because we have assumed this as a 0, and there's no more influx right after intake, and there's only outflux, which is proportional to the amount of the mass inside this system boundary, and that's accumulation rate. Just to note that this requires some basic understanding of simple differential equation of first order. So I'm gonna having an example of tracer, different kind of tracer, let's say, then we have to look at over time, it is x-axis, while y-axis is the relative concentration. So we put 3 different kinds of half-life, which means the time from the beginning to become a half of this concentration. That the duration of the time can be 1 minute, 15 minutes, and 180 minutes or 3 hours. So that's if these graph follows a simple first order kinetics, then it's a good idea to convert this one into a log scale, because the log scale will make it as a linear graph, which simplifies the understanding of this. Now I'm gonna start to build exercise for this. Okay, so just a very simple this tracer balance equation. Let's see. Tracer balance problem. So what's given is the half-life of 1/1580 minutes. So T half-life as 1/15/180 minutes. So based on the systems approach, as a accumulation equals influx minus outflux plus generation minus consumption. So here we know the influx is 0 over like when time is bigger than 1, and generation consumption is 0. And this becomes the mass of the change of the mass inside the system will be minus Km. Okay, or we can change it into concentration using C. Then that's so you can change this dC over dt is equal to minus Kc. Then we can solve this problem by the 1. So 1 we can solve it because exponential function is differentiation gives itself. So this, the answer is Ct will become C times 0 times e to the minus Kt. So based on the half-life definition, we can calculate C over T half-life will become 1/2 C0 becomes C0 times e to the minus K tau. Let's say tau is a half-life. Then this will lead to 1/2 will be e to the minus K tau, or we can solve it by taking a log of left and right side, then minus ln 2 equals minus K tau, or the tau will be ln 2 divided by K. So if this is what we know, or we can now write down K equals ln 2 over the half-life. Okay, and then we can now have these Ct equals C0 times e to the minus Kt is, let's say, 2. And let's take a log of 2. Then what will happen? So log ln of Ct becomes ln of C0, which is a constant, minus ln of exponential is by itself minus Kt. So that's number 3. Then the if we are interested in ln, log of concentration is now becoming the first order function over t. So this will be easier to draw how as a linear graph. So over time, so this is semi-log plot, ln and c is c0. So depending on this, different k, and this becomes a linear graph. So which this will be used that if the reaction is really linearly first order reaction, if we want to confirm it, we can draw the experimental data over T over a log of concentration and see if this graph looks like linear. Okay, so we'll stop it here and then move on. Now, I want to discuss one more time about the aspirin problem. So this is quite relevant for us. So those who have any family member who suffer from a fever, then we take aspirin. So the half-life of aspirin or acetylsalicylic acid is known to be about 15 minutes. If 10 units of aspirin is orally administered, then how long does it take for this body to contain 2 units of aspirin by having known this half-life of aspirin? And you remember if you actually use the tablet, will have about 300 to 600 milligram. And we don't take it like every 15 minutes. We are supposed to take it like every 6 hours. Then the question, how the biological effects of aspirin can last for several hours. So that's, we want to discuss it here, and let's see our board exercise. Okay, so the aspirin problem. So now given the half-life of aspirin, let's say is 15 minutes. And we wonder if how long does it take for aspirin to 10 units become 2 units in our body. So let's see. So from what we know from the previous part, the proportionality constant K is defined as ln2 over tau. So we can write it ln2 over 15 minutes. Okay. So then the concentration, so let's see, CT equals C0 times e to the minus KT. So then the concentration of let's say D prime over C0 will be 10 units become 2 units. That will be, the time will be e to the minus KT prime, let's say. Then how can we calculate this? So KT prime will become ln5. ln5, or so we want to know the time of T prime will be ln5 so that ln5 divided by K, and this is 1, from 1, K equals ln2 ln5 times 15 minutes. So this you can calculate, and in fact this is about 2.32, so that will be about 3:35 minutes. Okay. So the time for the concentration become 10 to 2 units, which is 5 times lower. It takes about 35 minutes. Then if the 2 unit is effective concentration for aspirin to our body, then it only takes about 35 minutes. Then the efficacy of aspirin will not be effective enough. So that if I write it down in this graph, like, so 10 units, and so it's exponentially decaying and becomes 2 units. And what it means, it takes only about 35 minutes. And of course, half-life is 15 minutes. So how come the aspirin can be used last for several hours? And the answer is the biological effect will last as long as the concentration is above the therapeutic concentration. So we just have U as a very high and high, then therapeutic. So this is concentration. Therapeutic concentration can last for several hours by putting a huge dose of initial dose. So if large dose is administered, then the effect can last as far as the concentration is above the therapeutic dose. Of course, this has to happen assuming if this initial dose is not toxic. So aspirin is in fact, that's the case. Okay, so thanks for your attention, and this is, we will move on to next time for the another physiological system.